Mr. Carlson here, and today what we're going to talk about is components of vectors, or what your book calls vector resolution. So in this case, what we're doing is we're breaking down forces or velocities or whatever it is that the problem is giving us, and we're breaking it down into its component parts. So for example, let's say that we have a sled that's being pulled across the snow. So here's my sled. We'll make it like a toboggan like this. Here's a sled, and it's being pulled by a rope like this. Let's give some more ground for this person to walk on, by this stick person here, and they're pulling it this way. And let's say that we know that the force applied on the sled is equal to 58 newtons. So we know that this person is pulling this way with 58 newtons, but we also know that it's not perfectly horizontal. This force that the sled feels is not perfectly horizontal to the ground. In fact, it has an angle of about, let's say, 30 degrees above the horizontal. That's the angle at which this force is being applied to the sled. Now, if we think about this, we can break that force down into its vertical and horizontal components, because part of this force, right, is felt being pulled this way, and then some of the force is also being felt in the vertical direction. And so that's all we're doing, is we're taking this force and we're going to break it down into its horizontal component, the left and right component, and the vertical component, or the up and down part. Now, the way that we would do this, the way that we would figure that out, is we're going to use kind of what we were looking at the other day, using some trigonometry to figure that out. So what I'm going to do is I'm going to take this, this force vector that I have here. So I'm going to redraw it down here. I've got a force vector of 58 newtons, okay? And what I'm going to do is I'm going to break this up into its components, in that we know that it feels a force that is a horizontal force this way. So I'm going to label that as the force applied in the x direction. And then it also feels a force component that is in the vertical direction. So force applied in the y direction. So this here is just the force applied, 58 newtons. And I'm going to break that up into its x component, or the horizontal component, and the y component, the vertical component. And how we can do this is we're going to shift one of these two things around. What I can do is I can either take this component here and I can bring it over here essentially and make a triangle, or I could take this component here and bring that up like this and put that component here and make a right triangle. That way, either way would work. What I'm going to do is I'm going to take this vertical component here and I'm going to bring it over. So our triangle is going to look like this. So I'm going to have my 58 newtons here. I've got my horizontal component, force applied in the x direction, and now I'm going to go like this. We call this going from tip to tail. So basically the tip of this vector is connected to the tail of this vector. So right now I've got both the tails are connected to each other, right? The tail ends of each vector are connected. But what I want to do is take the tip of one and connect it to the tail of the other one. And that's exactly what I'm going to do. So the tip of my vertical or my horizontal component is going to connect to the tail. Whoops, I should do it. Let me do that again in a dotted line. The tail of the vertical component, like that. So this is the force applied in the y direction. So all I did was take this and I moved it over in order to make a right triangle, essentially. But it's still the same thing, still breaking it up into its two components. But now I can use some trigonometry to figure out what is the magnitude of this force and what is the magnitude of this force. In other words, how much force does the sled feel vertically and how much force does the sled feel horizontally. So let's come back down. Oh, and let's add also, we know that this angle here is 30 degrees, right? We know that this is 30 degrees. So now using our trigonometry here, so let me put this over here so we remember. SOHCAHTOA. So again, the sine of an angle is equal to the opposite side over the hypotenuse. Opposite of this angle, the hypotenuse. Cosine is adjacent over hypotenuse. Here's my adjacent side, again my hypotenuse. And so what we're going to look at here is, let's say we do the sine, okay, the sine of this angle that we know. So the sine of 30 degrees. If we were to do that, the sine of 30 degrees, so we know that the sine of this angle is equal to the opposite side over the hypotenuse. Here's my opposite side, F, my force applied in the y direction, over my hypotenuse, 58 newtons. 58 newtons. And so what I can do now, I have sine of 30 degrees, I have 58 newtons. What I can do is rearrange this equation to solve for my force applied in the y direction. So if I rearrange this, I'm going to have the force applied in the y direction is equal to the sine of 30 degrees times 58 newtons, or times the force applied here. And that would give me my vertical component. And now let's do the cosine of this angle. So if I were to do cosine of 30 degrees, that is equal to adjacent side over the hypotenuse. My adjacent side to this angle is the force applied in the x direction. So force applied in the x direction over 58 newtons. And again, rearranging this equation here to solve for the force in the x direction. So force applied in the x direction is equal to cosine of 30 degrees times 58 newtons. And so if I actually crunch the numbers on this, so sine of 30 degrees times 58 newtons, I just had it, let me redo it one more time. So that would be 0.5 times 58. This would be 29 newtons. And for this, for cosine of 30 degrees times 58, we should get about 50 newtons here. And so what that means is that if we come back up here, the sled feels 50 newtons of force just in the vertical, or sorry, not 50 this way, it's 50 over here. 50 newtons in the horizontal direction and 29 newtons in the vertical direction. Those are the component forces, and the resolved force, the actual force here, is 58 newtons at 30 degrees above the horizontal. Okay, let's do one more example here with an example with velocity instead of force. So let's say that we have, I thought I had an example, there it is. Let's say that we have a wind. So we've got some wind with a velocity of 40 kilometers per hour, and it's blowing towards 30 degrees. Again, we've got that 30-degree angle. Find the vertical and horizontal components of the wind's velocity. So again, just like before, it's going to be pretty much the same thing, except for this time we're not dealing with forces, we're just dealing with velocities, but it's still the same process in order to solve this problem. So we'll draw, here's our velocity, I should say, so our velocity of 40 kilometers per hour, okay, and it's 30 degrees above the horizontal. And so again, what I'm going to do is I'm going to break that up into this wind is blowing with a horizontal component and a vertical component. And notice I just automatically drew it from tip to tail this way. And so I've got a velocity, so I'm going to put a velocity in the x direction and a velocity in the y direction here. Those are my components that I've got, and we know that the angle is 30 degrees. And so again, just like I saw up here, for the vertical component, it's going to be the sine of that angle times the hypotenuse. Sine of the angle times the hypotenuse. So for my vertical component here, my velocity in the y direction is going to be sine of 30 degrees times this right here, 40 kilometers per hour. And my horizontal component, velocity in the x direction, is equal to the cosine of 30 degrees times 40 kilometers per hour. And we crunch the numbers on those, and we should get, move this over a little bit, for our vertical component, 34, oh, keep doing these backwards. For our vertical component would be 20 kilometers per hour. And for our horizontal would be 34.6 kilometers per hour. So that's how we would break up vectors into their components and then solve for those different, the horizontal and vertical values of those vectors.